lab was to determine the pKa, Ka, and molecular weight of an unknown weak acid. Along with this process, we were generating pH profiles of titrations of strong and weak acids with a strong base. This presentation briefly outlines our procedure, states our experimental results, and discusses the conclusions we found.
Working with a partner, we obtained a solid weak acid, hydrochloric acid, and set up the apparatus according to the figure in the lab manual. To begin part 1, hydrochloric acid was pipetted into a small beaker. Deionized water was added so the pH electrode was covered entirely. The pH and concentration of the solution was recorded. The burette was prepared with sodium hydroxide. The sodium hydroxide concentration was recorded as well. In increments of 1 milliliter, sodium hydroxide was titrated into the solution while the pH and volume were recorded until the increase in pH between increments varied by more than 0.2 units. Then the addition of sodium hydroxide was gradually decreased until the equivalence point was reached. After reaching the equivalence point, the addition of sodium hydroxide was increased until the pH was approximately 12. The same process was repeated, substituting acetic acid for the hydrochloric acid.
Using the weak acid obtained from our instructor, titration methods similar to those of part 1 were used to determine the equivalence point of our unknown weak acid.
Figure 1 represents pH versus the volume of base. This chart is the plot of a strong acid titrated by a strong base. The pH is plotted along the y-axis, and the volume in milliliters of sodium hydroxide added is plotted along the x-axis.
Here we have figure 2, and this represents the pH versus the volume of base. The chart is a plot of a weak acid titrated by a strong base, and like in figure 1, pH is plotted along the y-axis, and the volume of sodium hydroxide is plotted along the x.
Figure 3, again, is the plot of pH versus volume of base. The chart is the plot of my unknown weak acid, and it was titrated by a strong base. The pH is plotted along the y-axis, and the volume in milliliters of sodium hydroxide added is plotted along the x-axis. The pKa value was determined to be 4.70. Setting 10 to the negative pKa determines the Ka of 1.9953 times 10 to the negative fifth. The known Ka value of acetic acid is 1.8 times 10 to the negative fifth. Using these two values, the percent error was determined. The accepted value is subtracted from the result. The answer to that is then divided by the accepted value. The quotient of the division problem is multiplied by 100 to find the percentage. The percent error calculated for this lab was 10.85%. The pKa for the unknown was 5. Setting 10 to the negative fifth determines the Ka value to be 0.00001.
For a molar mass of unknown, we have 0.130 moles, and the liter is multiplied by 0.009 liters of NaOH, sodium hydroxide, and this is equal to 9.27 times 10 to the negative fourth moles of sodium hydroxide. Since the products and reactants are in a 1-to-1 ratio, the moles of sodium hydroxide also equal the moles of acid. Using 0.2001 grams per unknown acid divided by 9.27 times 10 to the negative 4 moles of acid leaves the molar mass at 215.86 grams per mole. The unknown acid is most likely potassium hydrogen phthalate. The pKa of potassium hydrogen phthalate is 5.51. The rough estimate of our pKa of the unknown in this lab was 5.00. The molar mass of potassium hydrogen phthalate is 204.2 grams per mole. This lab's unknown molar mass was 215.86 grams per mole. Although they aren't exactly the same, the values were the closest out of the possible options of our weak unknown acids. They're not exactly the same because some human errors could have occurred and calculated into the values. For the unknown weak acid and strong base, the error percentage was about 10.85%. In this example, and the error percentage was 5.71%.
This was the overall complete ionic and net ionic equations for the neutralization of hydrochloric acid with sodium hydroxide. And going through that, we find that sodium and chloride were spectator ions, and we're left with hydroxide and hydrogen, which yields water. And these are the overall complete ionic and net ionic equations for the neutralization of acetic acid with sodium hydroxide. And as you can see, it is mirrored down with water.
So why were there no pKa or Ka for hydrochloric acid? The pKa and Ka for hydrochloric acid was not determined because it is a strong acid. Strong acids do not have dissociation constant because they completely dissociate in the solution. The initial pH of the strong acid, which was hydrochloric acid, was 1.62. On the other hand, the initial pH of our weak acid, acetic acid, was 3. So they are different. Comparing the pH of the equivalence points, the pH of the equivalence point for the strong acid, strong base titration, was 3.33. The pH for the weak acid, strong base titration, was the equivalence point of 10.91. In comparing the number of moles of base required to neutralize the strong acid versus strong base, the number of moles of base to neutralize a strong acid was 8.75 times 10 to the negative 4th moles, and for the weak acid, the number of moles was 9.5 times 10 to the negative 4th moles.
And these are references